All right, so we're talking on day 2, or I guess lesson 2 from 6.1, about a thing called Eulers Method. Now, before we talk about Eulers Method, let's talk about Euler just a little bit, because he is actually a really important person in mathematics. He made a huge amount of contributions to mathematics, and almost half of them after he was totally blind. When this portrait was painted, he had already lost most of the sight in his right eye there. He had a rough life, but he was still extremely bright and extremely instrumental in what we call mathematics today. It was actually Euler, who originated the following notations. F of x, our function notation, the base of the natural log, or the natural number, e, for the 2.71828, pi, for the ratio of circumference to diameter of a circle. That's where pi comes from, by the way, in case you didn't know it. I, the imaginary number, the square root of -1. The summation notation, and the delta y, the finite change. So he came up with notation for all of these. Didn't come up with the concepts naturally for all of them. I mean, pi was back a ways before that, so was e. But he came up with a notation that became very popular, very easy to use, and helped to make huge advances in mathematics. Now, there are many differential equations. Remember, a differential equation is an equation that has a derivative in it that cannot be solved. If you cannot take the antiderivative of something, you can't solve the differential equation. But even though we may not be able to actually solve it, we can still find an approximate solution. While you can take the derivative of just about anything, finding antiderivatives, as we've talked about in the past, can be problematic with some things. They're a lot more difficult. They have to fit into certain patterns before you can actually take the antiderivative. I mean, we've looked at some of these, and we'll look at some of these throughout the chapter. And if they don't fit into those situations, then we're kind of limited in what we can do. But we can find approximate solutions, and we're going to practice with an easy one, doing Euler's method, the way that we're going to use to approximate it. But we can actually solve this one. We're going to start off with dy dx equals 2x. And of course, if we were to solve this, we would just multiply both sides by dx, and then integrate both sides, and we get y equals x squared plus 2, or sorry, plus c. Then we could use our initial value to plug in and find that the actual solution for this would be y equals x squared plus 1. So that's what we're going to get as our solution, or that's what we would have as our solution, but we're going to approximate it using this information. Guys, if you have to do any of these on the AP exam or on one of my tests, it's going to be an easy one like this, but you still have to go through and show all the work. All right, so what we're doing here is we're actually trying to build by pieces this function that this derivative came from. Since we can't, the reason we would use this was we could not find the antiderivative, so we're going to build the antiderivative, or at least a graph of it, or a representation of it by pieces. So we're going to start off with our original point, the point that we're given, and n here is just the number of iterations, the number of times you've gone through the process. This is something where you're going to do the exact same thing over and over and over each time. So we're starting out with a point 0, 1, and we want to find out what dy dx is at this point. Well, that means all we have to do is plug in x for right here, and 2 times 0 is going to give us a dy dx. Sorry, we would plot that point to know where we're going to start on our graph. Then we would find our dy dx, and we're going to find out that when we plug in 0, it is 0. Now, Here's where you have to actually think a little bit. Remember what dy dx is. It's the slope. And if we take the slope and multiply that slope by some change in x, it's going to give us the change in y over that amount of x. So dy dx times dx gives us dy. So if we multiply the dy dx times some set dx, this will be given to you in the problem, or they'll give you a way that you can find out what it should be. Like they'll say from 0 to 2, break it up into 4 iterations. Well, 2 divided by 4 would give you 0.5. Either way, you're going to be given some way to find what dx is supposed to be. And then all you do is you multiply the dy dx value times the dx value, and that's going to give you the dy value. Well, what does dy signify? It signifies how much y changes. And then what you want to do is you want to find the next y value. So the way you find the next y value is you take the current y value, you add how much the y changed, and that gives you the new y value. And that's what this is down here. So in this case, 1 plus 0 gives me 1. So what this is it's the value, it's the y value for the next point. Well, what's the x value for the next point? Well, each time x plus dx, that's going to give me a 0.5 here and a 1 there. So after the first iteration, we had the point, 0.5, and 1. And then we just go through the exact same process all over again. Find dy dx for this point right here. So we're going to plug our point in. Actually, before we get started, let's go ahead and plot this point and connect it with a line segment. So we're going to go over here to 0.5. Still going to be a y value of 1. So we're going to connect those with a line segment. That's the first part of building our graph. All right, now let's go ahead and find dy dx. So we're going to have 2 times 0.5 gives us 1 for dy dx. Dy dx times dx gives us dy, 0.5. And then to find the new y, we're going to take the old y plus the dy gives us the new y, 1.5. All right, so the beginning of our next iteration, of iteration 2, we're going to have the point 1, 1.5. 1 being 0.5 plus the dx, and the 1.5 being 1 plus the dy. All right, so we would plot this point, 1 and 1.5, about right here, and draw our line segment. Now, go through and find dy dx for this point. We're going to plug in 1 up here to get 2 times 1 gives us 2. And then 2 times 0.5 is going to give us a dy value of 1. And then 1.5, the old y value, plus the change in the y, gives us the new y value of 2.5. So now in my third line, or third iteration here, my x value is going to be 1 plus 0.5, so 1.5. My new y is going to be 2.5. So I would go over here and I would plot that value, so I'm looking at right about in here, and draw the line segment. So we're expecting this to be a parabola, and it's looking parabola-ish, but it's blocky, of course. And it's going to be blocky because these line segments are kind of long. We'll talk more about that in just a second. So now let's go ahead and find, and we're going to finish this out until we get an x value of 2. We're going to go through this one and get the next point, and then we'll stop. So what is dy dx? Well, if we take the x value, put it in right here, 2 times 1.5 is going to give me 3. 3 times 0.5, dy dx times dx gives me dy. It's going to give me 1.5. And then my old y plus my new y, or plus my change in y, is going to give me 4. All right, so my next x value is going to be 1.5 plus my dx that was either given to me in the problem or information was given to me so that I could find what it would be. Typically, they're just going to say use a dx of 0.5 or 0.1 or whatever, and that's what you use. So 1.5 plus 0.5 is going to give me an x value of 2. I just found my new y value of 4, so we're going to have the point 2, 4. All right, so we go over here and plot 2, 4, and draw our line segment. So we are approximating this thing, the antiderivative of that, and when we do that, this is what we get. Now, our exact solution, as we talked about in the on the previous slide, would be x squared plus 1. Well, the graph of that looks like this. So you can notice that right here at the beginning, we're really close, but as we get away from that value, away from that initial value, our values get off a bit. So they're not going to be exact, but it is going to be a good approximation. Now, what's one way that you think we could actually get this to be more exact for a larger area? Well, we talked about how long these line segments are. The line segments go from an x value of 0 to an x value of 0.5, and 0.5 to 1, and from 1 to 1.5. So they're very wide. If we were to take this dx and make it smaller, then we're going to make a much more accurate graph. Now, that increases the number of iterations you're going to have for, say, an interval from 0 to 2. Let's say we had a dx of 0.1. That means we're going to have 20 iterations to get from 0 to 2. So that's not really going to work if we're doing this by hand unless we absolutely have to. But if you make a smaller dx, your approximation is going to be more accurate. And notice that the closer we get to our original value here, the closer our function value is to the actual value. Our approximation is to the actual function value. So this is called Eulers method, and as I said, it's more accurate if a smaller value is used for dx, and it gets less accurate as you move away from the initial value. All right, don't worry about any of the rest of this. That is all that you have to know about Eulers method. Like I said, if you're given one of these, it's going to be a simple one. You just have to go through the iterations and do the little things. They will not give you any equations on that, so you're going to have to remember that dy dx times dx equals dy. And you'll have to remember that y sub 1 plus delta y gives you y sub 2, the next y, and stuff like that. That's stuff you just have to remember.